All right, so ion-Lewis structures are just the same thing we've been doing with covalent compounds, just we need to figure out how do we draw the Lewis structures for ions. And we're using some polyatomics here because, remember, polyatomics, and we're using specifically polyatomics. Polyatomics. All right, poly means many, and atomics means we're talking about atoms. So when we talk about a polyatomic ion, that means many atoms together with a charge. And the important part, bless you, to remember is that this positive right here, what it means, right? That positive means that NH4 as a molecule has lost an electron, right? It gave one up, so it has one less than it would normally have. And so when we count our number of valence electrons, nitrogen has 5 for each of them, hydrogen has 1 for each of them. So 5 from that nitrogen gives us 5 plus 4 because there are 4 hydrogens with a single electron. But then it lost an electron here because of this charge, so we do minus 1. So our total number of valence electrons here is just 8 valence electrons. Now, the next step we do is the same thing as before. Nothing else is really different. We then do our central atom first, the first one. Then we put our hydrogens around it. I'm going to put them in a tetrahedralist shape. Then we put a bond to each of them. Now it's important to remember each of these bonds consumes 2 electrons. We did 4 bonds, so that's minus 8 electrons, and we're all out. So this is our Lewis structure for NH4 positive. Now the last important thing to change about this is because we had to do it with an ion, we go and put brackets around it, and then our charge on the outside. And that's the only difference between a polyatomic and a regular Lewis structure for a covalent compound, is just to add that last little thing for it. So if we look over here for SO4, we're going to do the same steps real quick. Sulfur is 6 electrons each, oxygen is 6 each, so we have 6 plus 24. And then that 2 negative means we gained 2 electrons. So we have a total of 32 electrons here. So sulfur, oxygen, 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 oxygen. Then we can do 1, 2, 3, 4 bonds. I'm going to use a slightly bigger pen. So we've used up 8 electrons. So 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That's all of our electrons. We've used them all up. We put our brackets around it and put a 2 negative out here, and we are done. That's all it is for polyatomic Lewis structures. All right, so one other thing, I am recording by the way, is bond polarity we're going to talk about. So with covalent bonds, there is a term called polarity which can come into play with different types of covalent bonds. So covalent bonds share electrons. It's a tug of war, whereas when we said ionic bonds transfer electrons. Right? In covalent bonds, it's very important that we realize that they're sharing the electrons. That's why when we look at them, so like carbon dioxide, we can count, when we count the electrons, we count 2, 4, 6, 8 for oxygen, so that gives us 8 over here for this oxygen. Then we can also count these bonds again for carbon, so 2, 4, 6, 8 for carbon, because we counted these bonds over here. We counted them twice. We counted them for both the oxygen and for the carbon because they're sharing them. Those electrons count towards both of them. It's kind of a tug of war. They're both pulling on the electrons, and the electrons kind of chill out in the middle between them. Now, that's not always going to be perfect. There are going to be two types of covalent bonds here. We have polar and nonpolar, right? Nonpolars are the simple ones, when atoms pull equally on the bonding electrons and they share them equally. The most common example for this are your diatomics. So like N2, H2, O2, that Brinkelhoff we talked about. And the reason these shared equally is because think about it. If we draw the bond for N2, it's N triple bond and then lone pair on each. These electrons in the middle that they're sharing, they're being pulled by this nitrogen, but they're also being pulled by this nitrogen. And neither nitrogen is going to really pull stronger than the other one. They're both the same thing. So neither one's really going to have an advantage when it comes to anything. They have the same electronegativity, they're the same element. It's going to share them equally between them. Other types of ones that we could talk about would be CO2, like I drew up above, CO2. Overall, this entire molecule, if you cut it down the middle here, it's the same on both sides. So overall, the molecule is going to be nonpolar. On the other hand, when we look at polar compounds, this is when electrons are shared unequally. And this is because you have some elements that are more electronegative. And remember, electronegative means how strongly they attract electrons. Or so how strongly attract electrons. Right? So the more strongly that atom or element pulls in these electrons, the more it's going to hog those electrons in that shared bond. The electrons are going to spend a little bit more time with that element. An example of this is water. And if we look at that, it's because when we draw out water, we have H, O, H, and then the lone pairs. So there's two signs here that this is polar. First off, these lone pairs over here are negatively charged, so they have a partial negative charge. And that tells us that it is polar because there's a negative side, and then there's going to be a partial positive over here. And then also, something we're going to talk about in a moment, oxygen is much more electronegative than hydrogen, which is going to mean that in these bonds here, it's going to pull on those electrons a fair amount more. So how do we know if something is polar or nonpolar, and how can we determine polarity? And these are my notes from earlier. Let's get out of here, notes. We'll make these a little bit neater this time. So there are a couple of main things that tell us if something is polar or nonpolar. So the biggest indicator is if there is a non-bonding or a lone pair, also as we call these, lone pair, right, on the central atom. So like when we look at water, so O, H, H, dot, 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 dot for lone pairs. These lone pairs here, because they're electrons, it's a concentration of those electrons. So that means there's going to be a concentration of a negative charge there. With that concentration of the negative charge, that there alone tells us that there is not the same charge everywhere. One important thing to remember about what we mean by polarity is polarity, you can think of the poles on a magnet, right? You have a north and a south pole, right? With magnets, there's actually a magnetic field going like this, right? It goes out this way, around, around, and then back in over here. So with that, we call these poles because they are polar opposites. They're two very different things. It has two sides that are very different from each other. The north side is very different from the south side. The north side pushes out, the south side pulls in. So that's why we call them poles. The same thing happens with polarity. When we say something is polar, that means it has two very different sides, distinct sections. If you think of our planet, when it comes to our geography, we have a North Pole and a South Pole because they are the two very distinct points and ends of our planet. So when we talk about polarity, polarity is something where the charge creates two very distinct parts. So specifically on water, you have a negative charge up here and a positive charge down here. The other way that we can see this is if it is symmetrical. So if something is symmetrical, that means it's non-polar overall. Because if it's the same on all different sides, no matter how you cut it, such as with methane, no matter how I cut methane or cut it in half in different directions, if I cut it this way, straight down, or straight across, on either sides of the imaginary line that I'm cutting, it's the same on both sides. So those two separate sides are going to be pulling on the electrons evenly, so it's going to be shared between them evenly. And then lastly, the way that we can see if something is polar or determine whether it is nonpolar, polar, or ionic is depending on the electronegativity difference of the elements in question. So if the two elements in question have a very big electronegativity difference, that's going to tell us that they're either polar or ionic. If there isn't a really big difference, that means that they're going to be pulling on the electrons about the same, so they're going to be very nonpolar. And how that works is if they have an electronegativity difference of 0.4 or less, they're nonpolar. And that 0 happens a lot when we think of like our diatomics, such as Br2. If I have Br bonded to Br, the difference in their electronegativity is going to be 0 because they're the same thing. A polar example would be, let's look at our little handy dandy periodic table right here. If we had carbon bonded to fluorine. So notice how fluorine has an electronegativity of 4.0, carbon has an electronegativity of 2.5. So between those two, they're going to have a difference of about 1.5 on the scale for their electronegativity, which is less than 2 but greater than 0.4. That is what causes them to be polar, right? Fluorine is going to pull much more strongly on those electrons than carbon will. And then lastly, ionic can also be determined based on an electronegativity greater than 2. The easiest way to determine if something is ionic is if there's a metal, but you'll also notice that those metals over here, so our metals, aluminum, gallium, tin, lead, all these over here have incredibly small electronegativities, all the way down to 0.7. So anytime they bond with a nonmetal, you're going to end up with a very big electronegativity difference, which tells us whether it is ionic, polar, or nonpolar. So just to show a couple examples real quick, let's say that we have, hold on one second, let me do this example real fast. Let's say that we have hydrogen and bromine. With hydrogen and bromine, right, hydrogen is up here. It has an electronegativity of about 2.1. Bromine would have an electronegativity of about 2.8. So the difference between them is only 0.7, which is greater than 0.4. So we would say that this is not ionic, it is polar, right? Potassium and chlorine. Potassium is 0.8. Chlorine is, not that one, 2.5, which gives them a difference of, whoops, I did the wrong one. That's carbon. Chlorine is 3 and 0.8, so that gives them a difference of 2.2, which is ionic.